That works. Okay, that's good. Brightness. Okay, sweet. Cool. Hi everyone. My name is Denise, as Tatiana said. I'm maybe going to stand off to the side and not directly in front of that. So for the next few minutes, I put together a talk about Docker. One thing that kind of annoys me about most introductory talks to Docker is that people talk really heavily in analogies, and I think that analogies are useful, but only until they're not, right? Like, I think that to really grok Docker, you do need to engage a little bit with what's happening under the hood, I'm going to explain what I mean by under the hood. So my goal in the next 20 minutes or so, 20 to 30 minutes, is to provide you with a high-level understanding of what's happening on your computer when you use Docker. And I'm going to slightly touch on how to use Docker, but I'm not going to go into that in great detail because there are honestly tons and tons of resources online, and they're going to do a way better job at walking you through it than I will during the course of the talk. So I'll point you in the direction of some good resources, but this isn't going to be like how to use Docker, how to Dockerize all of your applications at the end of this. So that out of the way, welcome to this talk. It's titled Just Containerize It, and it is a beginner-friendly introduction to Docker. My slides are over there. You can download them, or you can go to slides.com and find them at the end of this talk. So to begin, I think that, so I made this word cloud. No? Okay. So Docker's a bit of a fad right now. Like, everyone seems to be talking about Docker, and it's on like every job description ever. I think with all these buzzwords going around, like infrastructure as code and like continuous integration and things like that, it's a little easy to get overwhelmed by the seemingly endless amount of knowledge you need to wrap your head around using Docker and what its purpose is. So I'm going to try to break it down a little bit. So the first place I went is Google. What is Docker? Docker is a person employed in a port to load and unload ships. Okay, that's really useful. That's not actually useful. So, but the shipping analogy is, I think, one of the more valid ones. So you can think of a lot of Docker's imagery is around shipping containers, such as this one. It's not a coincidence that Docker uses shipping-related imagery, right? So like in real life, these things are standardized all over the world, so you can take one of these off any port, put them on another port, and assume they're all going to stack neatly, regardless of what is inside. So that's sort of like the portability aspect that Docker is going for. The idea is that you should be able to transport the contents of a Docker container to any machine, as long as that machine can run a Linux environment. We'll talk about that later. Anywhere in the world. So where did this idea of containers come from? It came from the Container Store. Duh! Archer. Sorry. So I'm going to spend a little bit of time talking about containers versus virtual machines and differentiating these two, because I think this is a really important distinction. So I'm going to cover some vocabulary. These are the 5 key terms. I'm going to talk about each of them in a little bit more depth, but roughly, you have your hardware, your kernel, your operating system, a thing called the hypervisor, and on top of the hypervisor, a virtual machine. These go from more physical to more virtual. You can also think of them as top to bottom getting more and more abstracted. So what's hardware? Hardware is the physical parts of your machine. It's your CPU, it's your memory, it's your disk drive. The literally physical parts that move electrons around and cause things to appear on your monitor, which is another piece of hardware. I think we, by having interacted with computers, we kind of know what this is. Over your hardware, the thing that makes all the hardware work together is called the kernel. So I went to DockerCon in Seattle a couple months ago, and VMware was there. VMware makes virtual machine technology, and they were handing out bags of popcorn. And it wasn't until like a week later that I was like, oh my god, kernels! Yeah! So what the kernel does, essentially, it manages access to system resources. It's no good just having hardware lying around with electronic circuits made. You need to intelligently manage how those resources are made are used because you have a finite amount of computing power, and you want to use electricity in a smart way. So over or around your kernel, it's a little bit different depending on what operating system you have. The best way I could think to explain what an OS is, in the most general term, is that it's the interface between the kernel and the user-facing applications. So it's kind of like a platform on which you run your applications. So with certain exceptions, most applications don't run directly on the kernel. It requires a little bit more abstraction and a little bit more infrastructure in order to have like a rich user experience. A lot of operating systems come with GUIs. Mac OS X obviously has a GUI. But when you go into your terminal, you can certainly interact with the operating system in a text-based way. They don't always come with GUIs. So when we're using virtual machines, in a lot of cases, we have a component called the hypervisor, which is an abstraction layer for running virtual machines and what we call guest operating system. So you have your host operating system, which is the thing that sits directly over your kernel, and it's probably the thing that you interact with when you're installing applications, on your OS X machine, on your Windows machine, whatever. But you can also run virtual machines on top of your normal machine. In order to do that, the guest machine needs to feel like it's a real machine. So when it sends out, when it says like, oh, give me this much memory, give me this much CPU, you don't want the guest machine talking directly to your host machine. You want it to sit over a hypervisor, so the hypervisor simulates all the normal responses that the kernel would give back to it. The benefit of a virtual machine is that you have a contained environment. I'll talk about this a little bit later. I'm rambling now. So an example of a hypervisor, I think the most common one that people will tend to have heard of is VirtualBox. VirtualBox is a downloadable piece of software that you can install, and on OS X, for example, you can run a Windows virtual machine inside of your computer. I do this a lot at work when I have to make things work in Internet Explorer 9, so it's great for that. So then what's a virtual machine? Essentially what a virtual machine is, it is a guest operating system with a dedicated user space and processes. Don't worry if you don't know what user space is. I'm going to cover that a little bit later on. So broadly, there are two ways that people run virtual machines. As I mentioned earlier, you can use a hypervisor to run it over a host operating system. This graphic is straight from the Docker website. We'll contrast it a little bit later with how Docker containers access system resources. Yeah. Cool. So the other way is bare metal. So has anyone ever heard of the term bare metal? Just a show of hands. Okay, so bare metal virtual machines work very, very similar to traditional virtual machines. The only difference is that they bypass the host operating system, and they have a hypervisor that sits directly over the hardware. This is a little bit confusing to me, and still is. But if you've heard the term metal, it means running virtual hardware without a host operating system underneath it. So the reasons why people might do this are, you might not like the opinions and conventions imposed by a host operating system. Like you might not like the way that Mac OS X manages system memory, and you might want to kind of roll your own and manage system resources in a different way. I don't know a ton about this, but I've heard that if you work on a team or you work on an application with serious scaling challenges and you need like every last bit of CPU or every last bit of RAM, sometimes what they'll do is they'll run things on bare metal. I think it requires a lot more specialized knowledge, and you need to understand the interaction between the kernel and the hardware a lot better. But it is possible. I've never really done it. So two drawbacks of running virtual machines in either case. The first is that emulating hardware is really expensive. You have to basically capture every single call that would have gone to the kernel, which then would have gone to the hardware, and instead you have to capture that and send back a response to the guest operating system, almost fooling it into thinking that it's a real operating system. And in a lot of cases, you don't need to do all this, right? You don't need a separate kernel space when all you want is an isolated user space, which brings us to the next question. What is user space, and how does that differ from kernel space? User space, if you've ever bought a new iPhone and you went into the memory and it's like, oh, this is like a 16 gig iPhone, and you go into the available space that you have, and you find that you only have like 14.2 gigs of actual space. So the reason for that is when they say you have 16 gigs of hard drive space, that counts both user space and kernel space. So part of what's taking up the space is the operating system, kernel processes, and things that you can't delete, because literally if you delete them, you won't be able to run the iOS operating system. What you can control is the user space. So this is your applications, your media, your files, all of that sort of thing. And you can control user permissions. So just like you can create multiple user accounts on a Mac OS X, what is happening is that Mac OS X is dividing it up into multiple user spaces, but all the users are still sharing the same kernel space. So like the underlying operating system behavior doesn't change from one user to another, just like the files you can access and the applications you can run change. So if you're someone who's trying to run an application using a virtual machine, the virtual machine solutions are quite expensive as it is. So what if we could have a virtual machine with only the bare minimum we needed to run applications, right? We don't need to worry about like designation of kernel space. All we want is a separate user space. So we want to go smaller, right? On the left is a scene from the show Portlandia. It's a really silly scene. They go into this coffee shop and demand smaller and smaller coffee, and at the end they're basically drinking coffee out of thimbles. And on the right is a set of mini huskies, which apparently they make now. I didn't know they were a thing. So here's where Docker enters. I ran this presentation at work, and the feedback I got on this slide was, that's not a real whale. So I think there are two general Docker use cases that I've heard of, at least. I think the main one is people use Docker to run applications in managed and predictable environments using immutable images. And we'll talk about images a little bit later on. In other words, like people use it for application deployment. Who's used Heroku? Yeah, cool. So if you've used Heroku, you've actually already used Docker. Because what happens is the Heroku daemon or whatever takes your application, creates a Docker image, exports a Docker image up to AWS, and runs that container. It's all happening under the hood, and it's, Heroku abstracts all of that away, but that is what's happening, and that's the reason why Heroku is able to almost, like take what's on your machine and just like get it up on the internet. Obviously, if you're using different frameworks, you have to worry about configuration and that sort of thing. But it's a really, really straightforward way to deploy applications, thanks to Docker. I've also heard of people using it as a very, very lightweight operating system. So in the case where you don't, like earlier, all you want is a separate user space. I have some friends who contract for a lot of different clients, and what they'll do is they'll set up a different Docker machine, and I'll talk about what that is, with Docker containers and images on each machine, one machine for each client, so that at the end of that contract, all of the client's applications are in that one space, and they'll just delete the whole machine, and everything's wiped from their computer, and they don't have to deal with it anymore, rather than like installing. Imagine if you have to install like 6 different versions of Ruby onto your host machine, right? Like that would be a nightmare, and managing all those conflicting dependencies. So what Docker is, at the end of the day, is it's one of many operating system virtualization implementations. Don't worry too much about this. This is just sort of a way to, I guess, like to place where Docker is in the abstraction hierarchy. So Docker is even more abstracted than, well, I guess it's at the same level of abstraction as a guest operating system, or a little higher than a virtual machine. So if you go on Wikipedia and type in operating system level virtualization, there are tons and tons of solutions out there already. Docker is certainly not the first, and it's not going to be the last. It's the most popular one. I think that's in part due to it's pretty easy to just get started with Docker, and there's a lot of documentation online, and it's open source. So what is operating system virtualization? It means that you share one kernel, you have one host operating system, but you just create a series of isolated different user spaces. So the key drawback here is that because you're not running a guest operating system, you have to use what's underneath the hood, which in this case is Linux. So anything that can run on Linux can run on Docker, and vice versa. But you have to do some extra work if you want to run like a Microsoft SQL server instead of Docker, for example. So here's what Docker looks like as Docker Engine kind of occupies the entire space where the hypervisor and the guest operating system used to be, and gives you direct access to applications. So what's actually happening here is that Docker containers talk directly to the Linux kernel. I'm not going to go into too much detail about that, but I'll just sort of leave it there and say that's one of the reasons why Docker is so good at resource management. Yeah, cool. So let's go through the different components of what is happening when you run Docker. So Docker has two parts, kind of like how when you use Git, you have your local Git commands, and you also have your remote Git repository. So it's very, very similar. On your local machine, you have a couple of different things. You have your client, which is your CLI that you interact with. You can ask it for help. You can use it to create Docker images. Your Docker daemon kind of is the thing that does all the hard work. It's the engine that interprets all your commands and turns it into processes in the background that package up images, build images, deploy images, and so on and so forth. So what's an image? So images are immutable, which means that they are unchangeable. Once you have an image built, you cannot modify it. If you want to make a modification to that image, you're going to have to make a brand new one and package up a brand new one. There's lots and lots of benefits to stateless computing and immutable processing, but I don't have enough time to talk about them right now. So the main distinction I want to draw, though, is that images are immutable. They are a snapshot of a file system at a certain point in time, very similar to a Git commit at a certain SHA thingy, right? So like if you go back to that Git commit, you know that the state of the system is going to be the same every single time, as long as no one's like force pushed to master. Containers, on the other hand, are the system process that takes that image and spins it up as a process. Every time a container spins up a new image, or sorry, every time a new container spins up an image, the container is going to have a unique process ID. Once you stop that container and once you kill that container and you want to run an image again, you have to spin up a brand new container with a brand new process ID. So containers are ephemeral, unlike images. Images are stateless. Containers are ephemeral, which means that they only exist on your computer while your computer is running for a certain given time in like this time-space continuum. And finally, the Docker host is the host machine that is running everything. So this is a Linux kernel, essentially. So a distinction I just want to drive home, because I was confused about this for a really, really long time. Yeah, images are static, stateless files that contain configuration information necessary to run an application. It's not the same thing as the application itself. You can pass images around just like you can pass around static GitHub repositories, and I can run it on my machine, and James can run it on his machine, and Tatiana can run it on her machine, and we can reasonably assume that it's going to behave the same every single time. So that's what images are. Containers, though, are the is the actively running process that is making that application or that image interactable by humans or by internet people or whatever. So the sort of analogy here, which I've already talked about a lot, is like images are to containers as GitHub repositories are to an instance of that application running on someone's machine at a given point in time. So let's talk about Docker Hub for a little bit. Docker Hub is one of many Docker registries. If you've ever heard of like GitLab or Bitbucket or whatever, like different versions of Git, GitHub is not the only place that you can use for version control. And you can also have like private instances of GitHub or GitLab if you wanted to. Docker registries are the same thing. They are repositories essentially for Docker images. Docker Hub is the official one run by Docker, just like GitHub is the official one for GitHub. Yes. So it's a one-stop shop for images for all kinds of software. You can download images for languages, frameworks, version managers, databases, operating systems, or any combination of any of these things, which I think is really, really cool. So the way that any Docker registry works is on the client side, you run a command called docker build. You can also run docker pull and docker run, but what happens is before that, actually. So when you pull down a GitHub repo, like you can reliably know it's going to be kind of the same, well, exactly the same at a given commit, right? So being able to get the same output given the input over and over and over again means that this is a pure operation. This is really significant when what you're trying to manage is an entire application. You don't have to worry about the state of your application or the state of your dependencies or how many CPU resources you have left or whether MySQL is going to crash on you. Like the image pulled fresh and run in a fresh container will behave the same time every single time. This is really significant when you're working on an application that needs to spin up hundreds, or maybe not hundreds, like dozens, or maybe hundreds of new instances at the drop of a hat in order to scale to meet web traffic. So what happens is it'll make a request through the Docker host to the registry if you don't have the image on your local computer. Just like if you don't have I think Ruby Gems does this. It looks on your local computer first when you say like gem install Rails or whatever, and if you already have it locally, it's not going to bother to go over the network. So Docker does exactly the same thing. If you pull a new Docker image, or if you tell it to run a Docker image, it looks on your local machine, sees that it's cached. We're going to talk about caching later because I think Docker does it in a really cool way, and then only makes the network call if it absolutely has to. Another cool thing, Docker's open source. There are various reasons for this, but I think it's really, really cool. You can go on there and look in the source code if you want to, and take a look at the issues that people are raising. Cool, so let's talk about the Docker client quickly. I'm going to kind of go through this part quickly because these slides are online and this is, no one has their computers and there's no point in doing this as a code along. So if you have Yosemite or later, you can run Docker for Mac, or otherwise you'll need to run Docker Toolbox, which runs through a virtual machine, which, again, is a hypervisor. So you can check if it works if you see this little whale in your top toolbar. If if you run Docker in the terminal, if it's installed, you'll see a bunch of different options for things that you can do. I think one of the more interesting things you can do is to try to run this basic image called Hello World. So what it does is it first makes a call out to see if it has the image before requesting from the registry. If it exists, it will see if it needs to invalidate any cached layers, which we will talk about in a second. And if not, it pulls the image down from the registry, saves it on your computer so it doesn't have to do it again next time, and then pipes the output over to the client so that the user can see what's going on. This is roughly what it looks like. You can go home and try running this on your machine later on. So just a few very common commands. Docker PS is how you view your running containers. So remember, these are the processes that exist in a certain time and space on your machine, unique process IDs. Docker images are the images you have cached locally, just like the Ruby gems you have already in your Ruby path or whatever. Docker run executes a container and gets the application running at the end of it. And Docker kill is how you kill a running container. If you want to see what else is out there, you can just run Docker or Docker help. So that's great. Like, we can pull other people's images, right? But that's not really interesting. The more interesting thing is how we can roll our own images and package our own applications and Dockerize all the things. So the key to all of this is the Docker file. This is a file that should live in the root of your project directory. And it essentially is just a set of instructions to build your Docker environment. The Docker daemon interprets this at build time, I guess. So what goes into a Docker file? Well, you need a base image. You need somewhere to start. I think most people are not starting from nothing because you want something at least like a very lightweight operating system that allows you to pull in dependencies, do like apt-get, which is the version manager. It's kind of like Homebrew for Linux. So it lets you load your system and application level dependencies. You can put in your application files, so all of your code snippets, your style sheets, views, whatever. Port mapping information, because imagine. So this is something that took me a while to get my head around. You need to tell your machine where to look for the running Docker container because if you run like Rails, for example, if I run Rails on my computer, it goes to port 3000, right? And we're all on the same network. Any of you can connect to my instance on my machine, but you have to know what port I'm running on. So you can put in my IP address and do :3000. The reason why that's the case is because I'm on a different machine than you, and we need to do service discovery kind of manually. So Docker basically is a separate machine, but it just happens to live inside of your machine. You still need to explicitly tell it what port you want it to run on. So it knows where to find the running application. And the final thing is that you give it an execution command so that after all the layers are built, the thing actually has something to do. So an anatomy of a Docker file, as you can see, I pulled this off of a work project. We start from a base image, which in this case is Alpine Node. It's a very, very lightweight distribution of Linux. We have various shell commands. So we have apk update, curl bash, whatever. We want to declare a working directory, which is basically we tell the Docker daemon, here's where you're going to look for your application. I think this is more for just like make things go faster so it doesn't look all over the place. Add and copy are ways to do volume mapping, which I'm going to talk about in a second. And the command it should be the final line. Once it gets to the command, it basically stops execution until you kill the application. So what is volume mapping? Well, volume mapping is when you expose a file or a folder between two machines, which means that there's two-way interaction. So if I were to change a file that's been volume mapped into my Docker container on my host, the Docker container would also change it, which means that I can run a Rails application inside of my Docker container and have it, go to it in the browser and everything, change the source code on my local IDE, so I don't have to like load RubyMine or Vim or anything into Docker. It's really, really cool. You don't need to rebuild the container every time. All of your normal build tools will still work. Grunt and Gulp, Watchify, whatever, will continue to work as expected. So I noticed that I thought this was odd when I first saw a Docker file because I thought, well, dry, right? Like, don't repeat yourself. We have duplicate add and run commands. The reason why this is because Docker has a very clever caching mechanism. Images are like onions. They have many layers and smell bad, I guess. So the way that Docker caching works is that every line of the Docker file is a different snapshot of the container state. So if any file being mapped in has changed, every layer down will be invalidated. This kicks in when you're doing things like you update your package JSON. So what we do at work is we map the package JSON in before we map everything else, because the package JSON, running a diff on that one file is really cheap, but running a diff on your entire application is really expensive and takes a long time. So as soon as the package JSON change, that's a pretty good indication that the way that you're requiring your dependencies somewhere else has also changed. So at that point, you might as well just rebuild the entire thing. It's a really common pattern to use like and rm to one-line things, because maybe sometimes like you map in your credentials that you need to access AWS or your private npm-rc or whatever. So when you properly design your caching layers, I think after a while and you get some more experience, you can strike a good balance between having really fast builds most of the time and having a very slow build sometimes. If you find yourself doing the same thing over and over and over again, such as installing Linux and then installing Ruby 2.3 and then installing Bundler and then installing Nokogiri and so on and so forth, you can take advantage of Docker Hub's push function. So you can build your own base image and then push it up to Docker Hub, and then you can pull down from your own repository next time. It just saves you some legwork, and you can share your image among everyone that you work with so that everyone has the same base image. It's really handy if you want to avoid duplication of effort. And that's the command that you would do, a docker build and the docker push. So there's a couple of cool implications of using Docker, I think. So one thing that I took away from DockerCon was that the Docker team really envisions a world in which you don't have to install anything natively on your computer anymore. When I first heard this, I was like, whoa, like that sounds really weird, because I'm used to just having everything in my file system and knowing where I have to look. If my database gets corrupted, I know that I can export my DB files and then click it onto a new computer and then figure out what went wrong. The thing is, like, because these images are so small and so fast to spin up once they're cached, and if you're pulling things off of Docker Hub, you can see how many other people have downloaded it. So like, if 10,000 people have pulled an image, it's probably going to be reasonably high quality. You can start and stop any of these processes with literally one command, like one thing in the command line. So imagine like you want to just trial Rails, right? Instead of waiting forever for Rails to download on your machine and then not knowing exactly where things got loaded onto your global file system, just pull it all down in a Docker image and then experiment it with it inside of the Docker image. If it doesn't work out, if you hate Rails, just delete the container or delete the machine, and like you don't have to worry about anything that's installed in strange places on your file system. So what about persistence? As I said earlier, containers are ephemeral, so if you want to hang on to data after the container dies, so like a really good example is if you are running a Postgres image and you want to hang on to that data after you stop your application, you'll have to do a little bit of extra volume mapping. I don't have enough time to talk about it now, but if you're interested, there's a tutorial on the Docker website that you can look at for Docker volume management. So, getting to the end now. No talk about Docker would be complete without mentioning what is possibly the best tool ever, Docker Compose. So Docker Compose comes for free with Docker for Mac, and what it allows you to do is chain together multiple Docker containers at startup and kill all of them in sync, like bring all of them up together, put all of them down with one centralized YAML configuration file. I find this really, really useful for if you're working on microservices, if you have to like start up 16 different things just to be able to work, to run one query end to end. Or it's also really good for testing and monitoring. If you want to play with like the Elk stack, for example, Elasticsearch, log/Kibana, there are a lot of Docker Compose files out there. There's also like a hub somewhere. I don't know exactly where. Yeah, it allows you to play with things end to end and have multiple dependencies at the same time. And it does service discovery for you, so you can, this is a sample Docker Compose file. By service discovery, I mean like applications knowing where other applications that they need to talk to are without you manually telling it. Like, here's the IP address, here's the port number. Docker Compose allows you to abstract that away. You can just create links between your Docker containers in this YAML file. So you can look at that in more detail if you want later. This is an example of a app with many microservices, as you will, that you can spin up all of these things at the same time with just your YAML configuration. I think that's really cool. So what's this thing? Who knows what that is? Silo. In fact, it is a DevOps silo, which is a very naughty anti-pattern. Who here works in a place where you have a separate DevOps team or platform team or infrastructure team or something like that? Okay, I think most people do, because I think a lot of companies view that as like quite specialized knowledge. It's not wrong to have a DevOps team, but it is wrong when you work for a long time on a project and then it comes time to get it into the real live production environment. So you throw your project over a wall at the DevOps team and they do some magical things on AWS and randomly it's online and nobody who wrote the code actually knows what happened. So that's really, really bad because it means that your ability to get your code into production is totally blocked by this team. Right? Imagine you need to do a critical bug fix in production and all your DevOps people are on vacation. Like, that's really bad. I think what Docker is really handy for is that because everything that goes into Docker is code and it's configuration, you don't have to do anything manually through a web interface or anything like that. It helps break down the divide between dev and ops. I think configuring Docker containers is easier for developers to grok than it is for us to learn how to write custom XML Jenkins configurations and crap like that. So I think it's also really good because it allows you to share environments more easily and reliably. You can, as long as both people have Docker on their machine, doesn't matter if you're running Windows or Mac or Linux, everyone can assume that they're working with the same image and the same instance of the application. I think it also makes you think about dependency management because you need to write every dependency into the Docker file. I think this is good because random mysterious dependencies are often the source of security vulnerabilities, especially with web applications. I think this is just a good mentality to be in and having to think about what dependencies you actually need. And the final thing, as I mentioned earlier, is like scaling becomes really, really natural. You can configure AWS ECS, which is EC2 container service, to have built-in support for Docker. And literally with like one drop-down thing, you can say, I want you to give me a maximum of 8 containers or 8 processes if you ever need it. Docker 1.12 comes with orchestration, which is basically like an entire suite of DevOps tools. If you're interested in that, go Google for it. I think it's really, really cool, but don't really have time today to talk about it. And a lot of the common pipeline tools like Jenkins and CodeShip already have built-in support for Docker. So I wrote some trivia questions, and I have some stickers from GitHub, and also a very special limited edition pin from DockerCon in Seattle that Tatiana will hold up. So if you've used Docker at work, I'm going to ask you not to answer. Sorry, but we'll just see how this goes. So for the first question, which the lucky winner will receive a GitHub sticker of their choice, what is the only operating system that Docker runs natively on? There, right hand. Bibiana. Correct. Maybe just wait until the end and you can come up and pick a sticker at the end. Second question. What is the thing that emulates hardware so you can run a virtual machine? Yes, hypervisor. Well done. True or false? Docker images are stateless. It's a 50-50 shot. Docker images are stateless. Yeah, it's fine. Okay, final question for a sticker. What command shows you you're currently running containers? You answered already. Anyone else? Okay, go on. Docker PS. Ding, ding, ding. Okay, final question. And the person who gets this right will be the lucky winner of the Docker pin. Final question. What programming language is Docker primarily written in? Yes, in the back. Nope. Tatiana? Go. Yes, Golang! Amazing. All right, cool. So at the end, everyone who got a question right can come up and pick a GitHub sticker. That's pretty much it. Here are some resources. Oops. Here are some resources. If you're interested in exploring Docker further or checking out some tutorials, I did this tutorial and I thought it was quite helpful and pretty well written and explained. Yeah, my slides are online, so if you want to go back over any of these, feel free to. That's it. Thank you. Stop. How do I stop?
Pizza.